Sorry about that. Okay, one more time. So today's lab session is devoted to using contingency tables to find probabilities. These probabilities you may or may not have seen yet, depending on where you are at in lecture. I know this morning in my Tuesday-Thursday session, we were able to cover the probabilities. So the students that are in the Tuesday classes might have seen these already, which is great. If you haven't, again, it's not a big deal. I would like to start today's session by going over them with you. So we are interested in defining a number of different probabilities. These probabilities are as follows. So I'm just going to show you the screen here. Okay, so these probabilities are as follows. We have the union, we have the intersection, we have marginals, we have joints, and we have conditionals. In general, we are going to be interested in defining those probabilities using using our two-way contingency table. So that will be the focus of our illustrations today. All right, so as a reminder, a two-way contingency table looks something like this. Okay, so we're gonna have a row and a column label. And within each of those, we're going to have some kind of outcome, right? So we might have A here and B here, for example. All right, so let's say that each of these has three outcomes, right? So we'll call this A1, A2, A3. We'll call this B1, B2, and B3. Okay. So inside the table, we might have we will have a set of counts, or alternatively, we'll have a set of probabilities, but we'll talk about those a different time. Okay, so I'm just gonna extend my table a bit here. So let's try to get everything to add up to 100. Notice that this 100 here is our capital N. So if you recall from our probability discussion, well, the probability discussion you would have seen in your lectures, capital N represents the size of the sample space. All right, so let's say that here we have 20, here we have 10, here we have 10, that's 40, here we have 5, here we have 5, here we have 10, that's 60, 10, 20, 30, 50, 60. And then I need another 30, so we'll go 10, 10, 10. We'll try and keep the numbers nice and even. All right, now we can row sum and column sum for each of these. Okay, so here we have 20 plus 15, which is 35. Here we have 25. Here we have 30. Here we have 30. Here we have 20. And here we have 40. Okay. So 35 plus 35, that is, oh, hold on a second. No, this adds to 90. So I'm missing something. 20, 40, 60, oh, 90. Sorry, one sec. Let's make this a 10. And let's make this a 15. Okay, so this is a 30. And then this is a 30. Okay, there we go. Okay, so let's start with, well, we're gonna work a little bit out of order here, but we'll start with, say, a marginal probability for an example. Okay, so the marginals are actually just the row or the column sums within our contingency table. So if we were to highlight the marginals here, we would have these values representing different possible marginal distributions. 35 row B3. Yeah, thank you, Rebecca. Yeah, thanks. Okay, so let's say, for example, we wanted to compute, well, we have 6 different marginals here, right? So we can write this as probability A1. This is going to be little f over capital N. which is 40 over 100, which is 0.4. Okay, probability B2, little f over n, which is 30 over 100, which is 0.3. And then one more, probability B3. This is going to be little f over n, which is 35 over 100, which is 0.35. So these are 3 different examples of marginal probabilities. Now let's talk about the joints, because those will be the next things that we need. Because this is going to be 4 here. Okay, the joint probabilities are actually just the values that exist inside the table. So in this illustration, we're going to have 9 potential joints that we can compute. But depending on the number of outcomes in our contingency table, we can have a differing number of joint and marginals. And we'll see an example of that when we switch over to the R Commander screen. Okay, so let's say, for example, we want a joint, which is the same as the intersection between A1 and B1. Okay, so this is going to be little f over n. A1 and B1 is going to be this first 20 over 100, which is 0.2. And then let's say that we want probability A2 and B3, for example. Okay, this is going to be little f over n, A2, B3, that's going to be 15 over 100, which is 0.15. And then let's say we want the joint between A1 and B3. Why not? This will be little f over n, which is equal to 10 over 100, which is 0.1. So those are 3 examples of joints. Joint probabilities, again, they're just probabilities that exist within the contingency table. So they are basically just values within the table that divide by the total size. Marginals are values on the row and columns that divide by the total size. Strict definition of marginal just means removing the effect of one variable. So when we look at the probability of A1, for example, that is summing across all levels of B to just focus on that A1 outcome. All right. Okay, now let's turn back to the first rule, which is union. Okay, so the union is defined in the context of a contingency table. We can almost always think of the general rule for a union as being the probability of A or B is equal to the probability of A plus the probability of B minus the probability of their intersection. And this is a rule where A and B are not related to the contingency table. So this is just a general formula. So don't confuse this general equation with the A and B listings that I used in the contingency table. Those will change and we'll see examples of that. It's, again, a general nomenclature. All right, so let's look at an example here. Suppose that we wanted the probability of A1 or B1. So we would have probability A1 plus the probability of B1 minus the probability of A1 and B1. Okay. Oh, sorry, I should be consistent here. This symbol here, that little cap that I had, that means and. There we go. And B, okay, and then I'm using capitals, so I should use capitals all the way through. Okay, so we're gonna have P of A1, which is 40 over 100, plus P of B1, which is 35 over 100, minus P of A1 and B1, which is 20 over 100. All right, so that's going to give us 75 minus 20, 55 over 100, which is 0.55. Right? So the union, in the context of a contingency table, because you almost always have no situation where there's a zero count inside, is going to be found by taking the marginal, adding the other marginal, and then subtracting the intersection. And that's done through equation 1 here, which is called this general addition rule. And we'll learn about that. If you haven't seen it already, you will learn about it in lecture. Just a general formula for computing unions when intersection exists. Okay, let's look at another example. I'm going to just take the contingency table with us so I don't have to you don't have to be shifting up and down the screen. Okay, sorry, 1 sec. Okay, so let's say that we wanted the probability of A2 or B3. This is the probability of A2 plus the probability of B3 minus the probability of A2 and B3. Okay, so this is going to be 30 over 100 plus 35 over 100 minus 2b3, 15 over 100. Okay, so that's going to be 30 plus 20. That's 50 over 100, which is 0.5. Okay. And then another example, since we're doing triples today, let's do A3 or B1. So this is going to be probability A3 plus the probability of B1 minus the probability of A3 and B1. Okay, P of A3 is 30 over 100. P of B1 is 35 over 100. A3 minus B1 is 10 over 100. Okay, that's going to be, again, 55 over 100, which is 0.55. All right, so those are 3 different ways of computing unions using a contingency table. So row plus column or column plus row, depending on how we set it up, minus the corresponding joint on the inside. Oh, cool. Okay, so actually, I double counted one of the topics here. So for 4, this is actually the same thing as 2, which is intersection. All right, so these 2 examples are the same. All right, so the last thing we need to define is the conditional. Okay, so here we have the conditional probability. So the general rule for a conditional is the probability of A given B. So this here is pronounced given. This is the probability of A and B divided by the probability of B. So the conditional probability is a probability that computes the outcome of one value conditioned on the space of the other. Okay, so the general formula writes A bar, this horizontal bar, B, where the bar means given. So we would read this statement as the probability of A given B. The mathematical formula for this is the joint of A and B divided by B. So you can see that we have B on the condition, B in the denominator of the fraction. If you were to write the probability of B given A, you would have the probability of B and A over the probability of A. And notably, the probability of A and B is equivalent to the probability of B and A. Those are the same value. Okay. All right, so let's look at an example of this. So let's do the probability of A1 given B1. Sure, why not? So this will be the probability of A1 and B1 divided by the probability of B1. Okay, A1 and B1 is 20 over 100 divided by the probability of B1, which is 35 over 100, which is 20 over 35. Sorry, I'm just making a little bit of space. Just want to keep everything on one line here. And then 20 over 35 is equal to a number 0.571. All right, if we were to do the probability of B2 given A3, we would have the probability of B2 and A3 divided by the probability of A3. Okay, so B2 and A3 is 10 over 100 divided by the probability of A3, which is 30 over 100, which is 10 over 30, which is 0.3 repeating. And then finally, we have the probability of A2 conditioned on B2. This is the probability of A2 and B2 divided by the probability of B2. Okay, so A2 and B2 is 10 over 100 again. The probability of B2 is 30 over 100. Oh, same numbers. 10 over 30, 0.3 repeating. Right? Okay, so those are examples of the, well, 4 different probabilities that we will be interested in computing using a two-way contingency table. So we have the joint, which represents all the probabilities within the table. We have the marginal, which is basically represented by the row and the column sums. We have the union, which is marginal plus marginal minus joint. And then we have conditional, which is joint divided by marginal. Okay, so these 2 pages are very basic illustrations of those 4 probabilities. And for each probability, we looked at 3 examples. On assignment 3, effectively what your task is to use R Commander to construct a contingency table and then use that contingency table to define these very probabilities. These very probabilities, not a great sentence. To find the probabilities that we illustrated at the beginning of this lab section. So what we need to learn how to do next is build the contingency table, which we've actually seen examples of before, and then use that contingency table to find the probabilities that we are interested in based off of these rules, okay? So I'm gonna switch over to R Commander. Before I do that, does anyone have any questions about these initial examples? And here we go. Okay, share screen. Desktop 1. There is chat. Got my chat box up. Okay, and then here's R. All right, awesome. Okay, so let's open up R Commander. Can everyone see my R Commander page? Well, it's going to be up in a second. But can you guys see R and still hear me? Okay, sweet. Okay, so to illustrate the probabilities that we just saw, we are going to utilize the examples given in the demo questions on the Blackboard homepage. Right, so this demo question that we are working on is in the file fall, it should say 2020 on the website, demo questions. And we're going to look at question 7. All right, so this, I'm going to switch back and forth between this Word page, which you should see now, and then my R Commander page, which is shown here. So we're going to answer the questions in the demo file here using R Commander here. Okay, so we have recently statistics students at McEwen completed a survey. Raw data can be found in the file statistics student survey for R. You will create crosstab tables from this data set and calculate some probabilities. For all probability questions, include a probability statement and a solution in fraction, proportion, and decimal. Okay, so it's, you know, it's a bit taxing, but we'll work through the basics of it anyways. All right, so part A. In the data set statistics student survey for R, there are columns fed best, a variable that measures federal party a student views as having the best platform, conservative, green, liberals, or NDP. So we have 4 outcomes in fed best. So it's a qualitative value where you can answer conservative, green, liberal, or NDP. So there's 4 possibilities. And then we have JT good, our second variable, which is a variable that indicates whether a student feels Justin Trudeau is doing a good job as prime minister, yes or no. So we have a qualitative variable with 2 outcomes on JT good. So we have 4 for Fed best, 2 for JT as prime minister. Find the totals for each of the outcomes in the Fed best column. Find the totals for each of the outcomes in the JT good column. Make a crosstab table of the counts for each pair. Use this information to fill in the provided table by hand. Okay, so what we want to do is build a contingency table between Fed best and JT good. So we go to R Commander, data, import data, from Excel. This will be survey data. You can call it whatever you want. Spelled survey wrong. Click OK. So we have drip books, McKin, lecture, this, 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 and there it is. All right. Now if we click view data set, you can see that we have a data set with many different variables in it, right? The 2 variables that we are interested in, JT good, which is shown here, and Fed best, which is shown here. So we want to build a contingency table for this information. Statistics, contingency tables, that's nice. 2-way table, and then we select our row and column variable. So on the row, we will do JT good, but you could do Fed best. It honestly doesn't matter in the context of the problem. So we go JT good, where is J? There it is, Fed best here, apply, OK. All right, and here's our output. So we're going to take this table here. Oh, I guess we should also do summaries, frequency distributions. We don't really need to do this, but I guess the question is technically asking for it. So the question did say build a contingency table, and then it also said give the row totals. We can get the row and the column totals from the table, but just for the sake of completion so that we have full marks on any given problem. So we'll do Fed best. Oh, and there we go. And JT good. We'll click OK. All right, and here we go. Okay, so here are the counts for Fed best. So if we go back over to our table here, we can just stick those in. And here are the counts for JT good. So if we go back over to our R, we can stick that in. And then we have our contingency table, which we built above, which is shown here. Okay. Let me just make this a bit bigger for everybody. There we go. All right, so here are the summary of the counts. So using statistics, summaries, frequency distribution, I summarized Fed vote or Fed best, and I summarized JT good. That gave me these two contingency tables shown here. So that's my contingency table for JT good, and here's my contingency table for Fed best, or sorry, my frequency distribution for Fed best and JT good. And then the contingency table we built through statistics, contingency tables, two-way table, and then you just select the variables that you want, and that gives us the output shown here. Now I've just copy and pasted this into my Word document, which is given here. All right, now let's build the contingency table. So conservative no is going to be 10, green no is going to be 3, liberal no is going to be 1, NDP no is going to be 11, and then the total here will be all no votes, which are 25. Okay, conservative yes is going to be 5, green yes is going to be 2, liberal yes will be 23, NDP yes will be 5, and then my total here will be 35. Now each of my totals for the bottom I can find simply by adding the columns or the rows together, or I can just use the counts from the frequency distribution, right? So 15, 5, 24, and 16. And that gives us a total of 60, which you can find by adding the 2 row totals together or the 4 column totals together. Those should always equal the same number. All right, now we have a contingency table, just like the contingency table we saw in the earlier illustrations, and we constructed this using R. From this contingency table, we can define different probabilities. Part B, what is the probability that a student views the Liberal Party platform as the best platform and thinks Justin Trudeau is doing a good job? So here, what we have is probability yes and liberal. Okay, so we're asking for an intersection. Now the question is a bit wordy, but this is what we are looking for in this particular problem. Again, we have what is the probability student views the Liberal Party as best, and this is really the key, right? And means intersection. So whenever we see and, we should be thinking intersection, and thinks Justin Trudeau is doing a good job. Okay, so this would be answering yes to JT good and picking liberal as the best platform. So we have an intersection of yes and liberal. So if we go yes, liberal, that's 23 divided by 60, which is 0.383, which is 38.3%. Okay, so our probability statement is the first part in brackets here. So the question asks for the probability statement. That's P, yes, and liberal. Then it asks for the fraction. That's the 23 over 60. Then we have our decimal to 3, or we have our answer to 3 decimal places. And then we have our percentage. What is the probability that a student who views the Liberal Party as the best platform or thinks Justin Trudeau is doing a job? Okay, so here we have probability, student views Liberal as best, or thinks that Trudeau is doing a good job, right? So noticeably, between B and C, the only difference is that in B we have and, in C we have or. Or means union. So we're gonna have the marginal plus the marginal minus the intersection. And you can see here that this question is actually already completed for us. So we have P liberal or yes is P of liberal plus P of yes minus P of liberal and yes. So P of liberal is 24 over 60, that's a marginal. P of yes is 35 over 60, another marginal, minus the intersection of liberal and yes, which is 23 over 60. We found that in part A. That gives us 36 over 60, which is 0.6 or 60%. Any questions so far? Okay. Part D. What is the probability that a student who views the Liberal Party as the best platform thinks Justin Trudeau is doing a good job? All right. This question is trickier because of the wording as usual. So we have probability, student who views Liberal as best. So what we are saying here is that we are focused only on the students who have voted yes and JT good. Or sorry, we are focused only on the students who view the Liberal Party as the best platform. Okay, so we are conditioning ourselves into the Liberal column. We are focused only on the students that have voted or selected Liberal as the best platform. So we are asking, what is the probability that a student who is Liberal or voted Liberal, I shouldn't say they are, you're not a political choice, but a student who views Liberal as being best thinks Trudeau is doing a good job, all right? And then we would have here, thinks Trudeau is doing a good job, and we'll put this part in red. So this is going to be yes, given Liberal. So again, we've conditioned on the space of Liberal, student who views Liberal Party as best. So we are only selecting from students who view the Liberal Party as the best platform. Think Trudeau is doing a good job. So we would have probability yes and Liberal divided by probability Liberal. This is our probability statement. So that part is checked off. Now we have to complete the fraction. So yes and Liberal is going to be 23 over 60. That's going to be divided by the people that voted Liberal. It matters very much so. 1 second. Divided by the people who voted Liberal, which is 24 over 60. Okay, question. So why is it yes first? Again, when we condition, we are selecting a certain marginal as the space of interest. In this question, it says, what is the probability that a student who views the Liberal as best? So we are focused only on the students that are voting Liberal. So in total, we are only working in this column here, the Liberal column, which has 24 outcomes. And then it asks, what is the probability that any student voting Liberal thinks Trudeau is doing a good job? So that is the question. What is the probability you think Trudeau is doing a good job given you have voted Liberal as the best platform? So that's why the yes goes first, because we condition on the fact that we are only looking at students that have selected Liberals and then asking if they think or do not think. Well, in this case, if they think Trudeau is doing a good job. So it very much matters which goes first, because the condition, in this case Liberal, has to sit on the denominator of the problem. Okay, so this is our probability statement. This formula here that I'm highlighting, that's the conditional probability rule that I showed earlier on the written example. We have 23 divided by 60 over 24 over 60. That gives us 23 over 24, which is 0.958, which is 95.8%. All right. Okay, so in part E, now we're actually looking at the opposite. Okay, so probability, student thinks Trudeau is doing a good job. So we're only focused now on students that think Trudeau is doing a good job. So we're only focused on the students that have answered yes to JT good. And then we're saying views the Liberal as the best party. So in this question, we have Liberal given yes. Right, so this is going to be P, Liberal, and yes, divided by P, yes. This is going to be 23 over 60 again. Notice that the probability of yes and Liberal is the same as the probability of Liberal and yes. It doesn't matter which way you write a joint or an intersection, they always refer to the same number. Okay, and now we divide by the probability of yes, which we worked out earlier to be 35 over 60. Okay, so this is going to be 23 over 35, which is 0.657, which is 65.7%. All right, so this here, what we have seen is an illustration of how to construct a contingency table in R, and we have seen how to construct a joint, a union, or sorry, the probability of the joint, the probability of the union, and the probability of the conditional in two different directions. Okay. These questions include the probability statements. They include the fraction answer, the decimal answer, and the percentage answer. So whenever we have a question on a lab quiz or the lab midterm that asks for the probability statement, it's referring to something like this. When we have the fraction answer, it's looking for this, the decimal, and then the percent. Any questions? Okay, so let's keep working through this illustration. In part F, it says, in the same data set, there's a column gender identity. Let's do the same subset that we had before. So we want to partition federal vote against JT good, but we only want to consider the females in the data set. So to do this, we go to R Commander, we click Statistics, Contingency Tables, Multi-Way Table. So when we want to condition on a certain qualitative variable, like here we want to condition on gender identity, we click Multi-Way Table. We select our row variable, which is JT good. We select our column variable, which is Fed best. And then we select our control variable, which is going to be gender identity. Okay, and then we click OK. And then that pops out the following three tables. We are only interested in gender identity equals female. So we take this table here as our output. And we pop that in here. Okay. All right. So now, very similar to before, we can complete our table. So we have 6, 3, 9, adding those together. 3, 2, 5, adding those together. 1, 14, 15, adding those together. And 7, 3, 10. Okay, 6 plus 3, that's 17 here. 5, 8, 22 here. And then that gives us a total of 39. Okay, now we can basically do exactly what we did before. We're going to be following the same rules. Sorry. Okay, we're going to be following the same rules. We're just using a smaller contingency table. So what is the probability that a female student who views the Liberal Party as best and the operative word being and here, thinks Trudeau is doing a good job. All right, so this is going to be yes and liberal. All right, so yes and liberal is 14 or out of 39, 0.359 equals 35.9%. So you can see again, like really the R commander portion of this unit is very small. It's just contingency table construction, which is something we did learn before and we're seeing again now. For the most part, what we're really focusing on here is probability notation and calculation. So finding joints, finding marginals, and finding union and finding contingency tables. Or sorry, finding conditional probabilities. What is the probability that a female student who views the Liberal Party as the best thinks Justin Trudeau is doing a good job? Okay, so this is a conditional problem again. So we have probability, student who view the Liberal Party as best, right? So this is saying we're only focused on the people that have answered or that are in the Liberal section of our table. And then we have thinks Trudeau is doing a good job. So this is going to be probability yes, conditional on liberal. Okay, so this will be probability yes and liberal divided by probability liberal. This is going to be yes and liberal is 14 out of 39 divided by the probability of liberal, which is 15 out of 39. So that's going to be 14 out of 15, which is equal to 0.933, which is equal to 93.3%. All right, and then finally we have what is the probability that a female student who thinks Trudeau is doing a good job views the Liberal Party as best? So here we just have the opposite condition again. Okay, so we have P liberal given yes. Okay, so this is going to be P liberal and yes divided by P yes, which is equal to 14 over 39 again, but in this case we are dividing by the column total for yes, which is 22 over 39. Okay, that gives us 14 over 22, which is 0.636, which is equal to 63.6%. Hooray. Okay. All right, so okay, again, as a summary, we have talked about 4 different kinds of probabilities that we can extract from a contingency table. The focus of this lab and assignment 3 part B is this type of illustration. Build contingency table in R Commander, extract appropriate probabilities, but by hand. So we're not computing any probabilities manual or using R Commander. We are calculating them manually as we would on part A of the assignment. Okay, in the second question or in the latter parts of question 7, we have a gender that we want to condition on. We do that through the multi-way table command. In the first 5 parts of this section, we are just using the entire space of the data set to construct our contingency table. And then we have illustrations of different probabilities for those groups. Okay, so I'm gonna stop the teaching portion here. So I'm gonna turn off the recording at this point. And then for the rest of the lab session, I will be here to help with any questions that you might have.